Okay, so welcome back, everyone. Microphone is working again, wonderful. So in the first lecture from this tutorial, we started with well-founded relations and well-quasi-orderings. Are defined in terms of sequences, and the domain of sequences is the natural numbers, which serve as indexing set for the sequence. And then we saw in the example of this infinite power set construction that it can be useful to, instead of natural numbers or singletons of natural numbers, to consider pairs of natural numbers as indexing set. And now in the end, we took a huge step generalizing this further by considering, instead of just the two-element subsets, all the subsets of natural numbers, all the finite subsets of natural numbers identified with their strictly increasing enumerations. And then we saw this notion of block. And maybe just to illustrate this once more, a block is really the same as a bound on a well-founded tree. So if you have a well-founded tree, then if you take the things just below, just beyond the leaves of the tree, then you have a block. The things just outside of the tree, then you have a block. And conversely, if you start with a block and you take the sequences that are strict initial segments of the things in the block, then you get a well-founded tree. And now let's come to the notion of better-quasi-ordering finally. So first of all, I have to generalize this triangle relation that we saw before in the case of pairs. And okay, let's maybe write it down formally first. Let's consider some infinite set x of natural numbers ordered increasingly. Then by x minus, I denote the same set without its minimal element. So in other words, I drop the first element of this increasing sequence and start with the second. Right? And then if we now have finite strictly increasing sequences s and t, then we say that they are in the triangle relation if there is some infinite set such that S, the smaller one in the triangle relation, is an initial segment of this X, and T is an initial segment of X minus. What that means is, I think, best seen by example. So, for example, 1, 3, let's say 7 would be triangle below 3, 7, 15, 18, so they overlap. Triangle smaller sequences starts a bit earlier, and then the other sequence overlaps with it except at the first element. And it may go further. Actually, in a barrier, it will always go further. The right sequence in the triangle relation will always go further, but in a block, it could also stop earlier. But this triangle relation just means that the sequences overlap except for the first element. And now we generalize this notion of good indexing function, good generalized sequence from before, and we arrive at the notion of better-quasi-ordering, which is due to Crispin-Nash-Williams, as I mentioned before. So a quasi-order Q is a better-quasi-ordering if every array, and an array is just a function f that is defined on some block or barrier into the order, is good, in the sense that the block contains S and T, which stand in the triangle relation, and such that the corresponding values under F satisfy this inequality. So exactly the same as well-quasi-orderings, instead that you replace the natural numbers by these more complicated structures called blocks. And then there are two small facts that are maybe useful to prove in order to become more familiar with the definition. The first one is this is actually a strengthening. So every better-quasi-ordering is a well-quasi-ordering. And the reason is just that the subset of natural numbers that consists of all singletons is also a block. So well-quasi-orders are associated with sequences indexed as usual by the natural numbers, but you can also view the natural numbers as a block by identifying every natural number with its singleton. Maybe I'll leave that as an exercise to write it out rather than putting it. But let's maybe write down the second property. This is that all these notions coincide in the linear case. So if you have a linear well-order, then this will always be a better-quasi-order. And this works as follows. So let's assume we have some well-order alpha. We want to show it's a better-quasi-order, so let's do this by contradiction. So we assume that an f going from some block into alpha is bad. But now you start picking some sequence S0 in the block, and then you just pick anything that's triangle larger. And why do you find something that's triangle larger? Well, just take any infinite sequence X that extends your S0, drop the first element of that infinite sequence to get X minus, and then since you have a block in this X minus, you must have some initial segment that belongs to the block, and this is your S1 that stands in the triangle relation with S0. You can always pick something that's triangle larger, and then you can do that again, and you continue indefinitely. But if this f is bad, that means that whenever you have two things in the triangle relation, you cannot have an equality of the values in alpha. So then f of S0 is not below f of S1, is not below f of S2, and so on, right? Because of the assumption that f is bad. That would make it good if you had one of these inequalities. But now alpha was assumed to be linear, so if you don't have this inequality, then you will have a strict inequality in the other direction. So then you will have a strictly decreasing sequence in alpha against the fact that alpha was assumed to be a well-ordered. But it's really linearity, of course, that turns these non-inequalities into the converse. Maybe just two remarks that I maybe forgot to make earlier. First of all, if you write it down like this, this looks like the triangle relation was very complex on a logical level because you quantify over this infinite x. That's of course not necessary, right? Whether two sequences overlap, you can just see. You can decide. It's just convenient to write it down that way. And secondly, being a block is a pi11 property, because you say for every infinite set, something arithmetical happens. And here you have this property of being a block in the premise. So you're saying for every f, if the domain of definition is a block, so you have pi11 in the premise. So overall, this notion of better-quasi-ordering is pi12, because you have the for all f, and then the pi11 in the premise turns into a sigma 11, so it's pi12. And I better show that in fact it's pi12 complete. And in contrast, well-foundedness and also well-quasi-ordering are pi11 because you only quantify over infinite sequences and do nothing else. So you have brought up the logical complexity. Let me write that down because it should be on the slide, I feel. So being bqo is pi12 and in fact pi12 complete. Why is it defined in terms of x? It's just a convenient way to say that the two sequences overlap. We'll also see the x minus construction again later. You really don't have to write it down in terms of an infinite sequence. I like the shortest thing that I could put in. Okay. So now earlier we saw this power set construction, and that correspondence also generalizes. So instead of taking a single power set, we can now iterate the power set operation. And as you know, if we iterate the power set operation, we get the set theoretic universe. And here we are starting with some given order Q. So we are now building the set theoretic universe with the elements of this given order Q as OR elements. And it turns out that for what we want to do here, it suffices if you take hereditary countable sets. You don't take the full power set, but you only take countable subsets in each set. And then we order this essentially as we ordered the power set. Namely, we do this following. If we want to compare two of these sets with elements here, where we have different cases to consider, if they are both elements from the given order Q, then we compare them just like with the given order relation on Q. If we have two things that are not elements, so that really are sets that have elements, then we compare them as in the definition of the power set relation. So a set X will be below a set Y when every element X prime of X is bounded by some element Y prime of Y. And then we have to decide what we do in the mixed cases when one of them is an element and the other is not. And if you want to memorize the definition, then I think the easiest explanation is that we identify every element with its singleton, right? And what comes out of this is an element lies below a set Y if it lies below some element of that set Y. So we drop the singleton brackets around the element. And conversely, a proper set X lies below an element Y if every element of X lies below that Y. And again, we have dropped the singleton brackets around the element and taken the element as its own only element. So then these two here are instances of the other case. And then it turns out that what we had before generalizes. So before we saw that if you take bqos but defined only with respect to this barrier of two element sets, then that corresponds to one application of the power set operation. And more generally, if you take arbitrary better-quasi-orders, then that corresponds to taking all these iterations of the power set operation. So an order Q is better-quasi-ordered if and only if these sets with elements form a well-quasi-ordering. And then it turns out that this is also equivalent to these sets with elements being a better-quasi-ordering. So in general, being well-quasi-ordered and better-quasi-ordered are of course not the same, but this H of Q has such good closure properties, this object, that well-quasi-order and better-quasi-order are the same in this particular case. And maybe this also motivates a little bit why we generalized from the two element, the barrier of the two element sets to arbitrary well-founded trees, so to speak, because if you are given two sets, then in a sense the well-founded trees will tell you in which way you descend to the elements, or to which element in which direction you descend through the set membership relation in that set. This fact here, in particular the direction that if Q is better-quasi-order, then H of Q is well-quasi-order, has a really beautiful proof, game-theoretic proof. It's really nice. So you have an infinite sequence of games where one player always copies the move played by the other player in the following game, and so on. It's really very nice. And you can also define this order in terms of a winning strategy. It's all very beautiful. If we have time tomorrow, I might show this, but probably we won't. And in that case, I can refer you to this introductory paper of Jan Pequeno that I mentioned before. It's really a beautiful proof. And then also in reverse mathematics, this equivalence here is itself equivalent to arithmetical transfinite recursion, as shown by David and Manka, which I guess makes some sense because comparability of infinite well-founded structures. There are other examples as well where we have equivalences with okay. So yeah, and once again, we have shifted complexity between the object. So this HQ is much more complex than the Q, in a sense, between the object and the domain of definition of the sequences. Because here in well-quasi-order, the object was complicated, but the domain of definition of the sequences was just the natural numbers. And here in better-quasi-orders, the object is less complicated, but the domain of definition are these arbitrary blocks, which correspond to arbitrary well-founded trees. I want to give you a second perspective on the definition of better-quasi-orders in terms of continuous functions on the space of infinite subsets of the natural numbers. So if you haven't thought of continuity in that context, you can just take this as a definition. If you already have your definition, then you will recognize this as a true fact. So a function f that takes as input infinite subsets of the natural numbers and outputs elements of, in this case, of some given order Q, viewed as a discrete space, is continuous or sigma 0, 1 definable, precisely if there is a block and a function on that block which gives you this function uppercase f, in the sense that if you want to determine the value of uppercase f on an infinite set X, then since this B here is a block, there will be a unique element in the block that is initial in that infinite sequence X. And then you take this value of lowercase f on the finite initial segment as the value of uppercase f on your infinite set. Right? So yeah, I mean, what continuity means is that if you have any infinite set, maybe seen as an infinite branch in this tree, and you want to know the value of your continuous function on that set, then that value must be determined by finite information. So there will be some initial segment of that infinite sequence such that you have the same value for every infinite sequence that extends this final initial segment down here. That's what continuity means. And so functions on blocks are really the same as continuous functions. In a sense, the block is the modulus of continuity. If you are given a continuous function, then the block you could pick would be the one that consists of all the smallest initial segments where values are determined. And then you have this alternative definition of better-quasi-ordering. So Q is a better-quasi-ordering if for every continuous function f, there is an infinite set X such that f of x is bounded by f of x minus. And remember that x minus was x without its minimal element. So the infinite sequence shifted by 1. And that corresponds precisely to the definition of the triangle relation that we had here, where the triangle smaller element was an initial segment of x and the triangle larger element was an initial segment of x. So that's certainly the easiest definition to remember, at least if you're happy with this notion of continuity. And maybe one way to see it is also, you could see this as sort of the real world definition, and then the one via blocks would be the way you represent this in reverse mathematics, because in reverse mathematics, maybe second order reverse mathematics, you can maybe not talk about all these functions, but you can talk about continuous ones via representations, and the blocks are sort of the obvious way to represent. The reason I'm showing you this is not only because it's a very nice and easy to remember definition, but also because of the equivalent fact. Now that you have this definition in terms of all continuous functions, you can also think about relaxing this continuity condition. And in fact, it turns out that if you admit not only all continuous functions, but even all Borel functions, then you get the same notion of better-quasi-ordering. And this is because of a theorem, I think due to Mathias, which says that if you have any Borel function like that, then it restricts to a continuous function on a suitable infinite. Which is kind of a version of the Galvin-Prickry theorem, right? The Galvin-Prickry theorem would say, if you have a Borel function here with maybe a two-element domain, then you would have some infinite homogeneous set where the values are constant. And in this version of Mathias, you are not trying to find a constant value, but you're trying to find a continuous restriction. And it was Steve Simpson who observed, in this case of better-quasi-orderings, that this would be a very useful move to maybe admit the Borel function. On the other hand, in the context of reverse mathematics, these theorems, Galvin-Prickry and so on, are equivalent to pi1 transfinite recursion, so they're extremely strong. And so you have to commit to some definition that you work with over weak systems. And this is typically the definition in terms of continuous functions or in terms of blocks. Now, as I'm not sure if it's the final thing, probably almost the final thing in this first part about better-quasi-orderings, I want to quickly tell you some things about Fraïssé's conjecture. And this will stay on a somewhat intuitive level, or hopefully intuitive level, but in any case without detailed proofs and sometimes without the precise definitions. But I hope that it will still make sense. So Fraïssé's conjecture from the 1940s, I think. So Fraïssé conjectured that the countable linear orderings are well quasi-ordered under embeddability. So what that means is if you have any infinite sequence of countable linear orders, then you will find one order in that sequence that can be embedded into a later order. Right? And this was proved by Richard Laver in 1971. Actually proved a somewhat stronger fact, namely that even the sigma scattered orders are not just well quasi-ordered, but better quasi-ordered. But I just mentioned this for completeness. Fraïssé's conjecture of what it says in the first two. The original proof by Laver uses something called the minimal bad array lemma, and I will not say what this is, but it's one of the central tools in the theory of better-quasi-orderings. Together with Fyodor Pakhomov and Giovanni Soldat, I've shown that this minimal bad array lemma is equivalent to pi12 comprehension. So it's really a very, very strong principle. And so it was open for some time whether Fraïssé's conjecture itself. It was clear that Fraïssé's conjecture is not equivalent to pi12 comprehension for reasons of quantifier complexity, but it was not clear where it could actually be proved. Then the best upper bound that we now have is due to Antonio Montalban from 2017, who showed that at least Fraïssé's conjecture can be proved in pi11 comprehension rather than pi12 comprehension. And the known lower bound is ATR0 due to Richard Shaw from the 90s. It's still not clear how strong Fraïssé's conjecture is. These are the bounds that we have, at least in the published literature. Yeah. So in the next few slides, I want to briefly sketch how Antonio Montalban proved this in pi11 comprehension. Before that, let me maybe mention a curious fact. So this equivalence with pi12 comprehension, I wrote that it's over ATR0. And in fact, the minimal bad array lemma is quite weak over ACA0. So it's one of these cases where over weak base theory, you don't get any strength, depending on how you formulate the minimal bad array lemma. But then over a somewhat stronger base theory, you reach very high. So about this proof of Montalban, how did he show in pi11 comprehension that the countable linear orders are well quasi-ordered? So the first very important ingredient is a representation of linear orders via signed trees. So trees where all the nodes are labeled by plus or minus. And in fact, these trees in Montalban's representation do not correspond to all linear orders, but just to indecomposable linear orders. And indecomposable means that when you have a linear order and you split it into a left part and a right part, then the full order will embed either into the left part or into the right part. Indecomposable. And how does this tree representation work? So let's say in something. Let's say you have a tree labeled by a plus at the root. On the slide it says plus / minus. These are the two alternatives. Let's consider the alternative with plus. And then you have subtrees T0, T1 above it, and so on. And what's the order that corresponds to this tree? So maybe the first thing that you could consider is inductively, these are well-founded trees. So inductively, you already know which orders correspond to T0 and T1. And then maybe the first thing you could try is you linearize T0, which you could do inductively, you linearize T1, and then you put these next to each other, and so on, and build a linear order out of that. And what you do is almost this, except that you repeat everything infinitely often. So you repeat the linearization of T0 infinitely often, and of T1, and so on. And on the slide, that's what this pi0 does. So pi0 is the left section of the Cantor pairing function, but it just serves to repeat everything infinitely often. And that's also what makes the order indecomposable, and what also makes things independent of the order of subtrees, which will be very important. That's the real reason that in the following, we don't want to consider trees where the children of each node are ordered, but where there's no order on the children of a node. And that's why you have to repeat these things so that the order doesn't matter, and that's why you get indecomposable. And if the label at the root is minus, you do the same thing in the other order. So the linearization of T0 is not at the beginning of the order, but at the end of the order, and then you go to the left, but you also repeat everything. And then it turns out that embeddings between these orders correspond to tree embeddings, and the tree embedding is a function from the nodes of the first tree to the nodes of the second tree, such that first the labels are preserved, so plus is mapped to plus and minus is mapped to a minus, and also strict extensions are preserved. So if in the first tree you have sequences s extended by t, then the values f of s should also be extended by f of t. On the other hand, you don't require injectivity. So yeah, you could map different sequences that are incomparable in the first tree to the same sequence in the second tree. And in particular, if you have worked with Pascal's theorem before, there you want your embeddings to preserve infima, and this is not the case. You just want to preserve labels and these strict extensions. Okay, and now you have two labels, plus and minus. And here comes a slightly technical point, but which will be very important later. So later you want to relax the condition on your embeddings even further and look at something called weak embeddings, where if s is strictly extended by t, you don't demand that the value f of s is strictly extended by f of t, but only that it's weakly extended. So they could be the same, right? So you could send two consecutive nodes, a node and its child, to the same node in the tree on the right, as long as they have the same label, right? Because the labels have to be preserved. But if a node and its child have the same label, then you want to be able to send it to the same node in the other tree. And this is something that you're not allowed here in the context of these linear orders, but you will want to do on the next slide. And the way you can do it is by introducing a third label. And then you just put this third label on every second level. And then even if you allow these weak embeddings in principle, you can exclude them by putting this third label, because the label still has to be preserved. And so if a node and a child have different labels, then they cannot be mapped to the same thing. This is how you only had two labels to represent linear orders, but then get a third label if you want a relaxed embeddability relation on trees. That will be important. You'll see that the two-element case and the three-element case are very different when it comes to better-quasi. Okay. And now, if you want to prove Fraïssé's conjecture about these linear orders, you can, by this work of Montauban, just as well prove the corresponding statement about the trees. So now you want to prove that, let's say, with three labels, but these weak embeddings, the trees that you get also form a well-quasi-order or better-quasi-order. And what Montauban showed is first, so we were initially looking at continuous functions. The pointer doesn't work anymore, so I'm using this broom now. We're first looking at continuous functions of the space of infinite sets into Q, and then I said that we could replace it by arbitrary Borel functions, And Montalban went up just one step in this Borel hierarchy and considered delta 0, 1 definable functions. And then he showed that if all these delta 0, 1 definable functions are good, then the trees with labels from Q form a better-quasi-order. Embeddings, and this can be done in ATR 0, and there's a partial reversal again by Davide Manca, which shows that what Montalban does is essentially the optimal thing that you can do. Not quite, but you know that it's close to optimal. I won't show you how this works, but I want to say that it's quite closely analogous to this result about the hereditary sets with Ur elements that we saw earlier. And the idea is that hereditarily countable sets with Ur elements, you can view these as well-founded trees which have the Ur elements at the roots. And you can, if you have a set, then you can turn the membership relation on that set into a tree, and the Ur elements will be the leaves. Right? So earlier, for continuous functions, these corresponded to embeddings on the set, so on trees with leaf labels, but no internal labels. And here we have trees with internal labels in this proof of Fraïssé's conjecture. And this corresponds to the fact that these delta 0, 2 functions correspond to functions on finite sequences that are eventually stable, but before they become stable, they may have incorrect values, and these incorrect values in some sense correspond to the internal labels in the tree. The continuous function doesn't have any internal labels, because for the continuous function, it's just sort of indeterminate for a while, and then when it tells you a value, that value is correct and you are at a leaf. But for the delta 0, 2 functions, you have first these incorrect values that correspond to internal labels. And that's a bit vague, but I think it's a good way to understand why delta 0, 2 functions come in here, and why the proof is also quite similar to the proof that I mentioned before, the game theoretic proof that this H of Q. And then the last step is to show, I previously mentioned that these Borel functions have continuous restrictions if you have pi-Borel non-transfinite recursion. If you only have pi-Borel non-comprehension, then you can at least go to these delta 0, 2 functions. And overall, this reduces Fraïssé's conjecture to the statement that the antichain with 3 elements is a better-quasi-ordering. So the way this works, maybe once again, is assume the antichain with 3 elements is a better-quasi-order, defined in terms of these continuous functions. Then over pi-Borel non-comprehension, you can upgrade the continuous functions to all delta 0, 2 functions. If you have this for all delta 0, 2 functions, you can go to these trees with internal labels, still 3 labels, but these weak embeddings. And sacrificing one of the 3 labels, you can upgrade to strong embeddings of these trees, but with 2 labels, plus and minus, and these represent the linear orders from Fraïssé's. So that's the quick summary. And I'd say there are 2 reasons why I wanted to show this, even though it was quite an incomplete description of the proof. One reason is because this is probably the most famous application of better-quasi-orderings. So if you want to see how this definition is motivated, this is a big part of it. The second reason is that in the following, I will talk about finite better-quasi-orders. And now you could think that these notions should be trivial in the finite case. I mean, for example, to see that a finite order is a well-quasi-order, that's trivial, because to be a well-quasi-order just means that you have to consider an infinite sequence, and then at some point you should get an inequality. But if the elements of your infinite sequence come from a finite set, then some element has to repeat, and then you have an inequality by reflexivity. So for finite well-quasi-orders are trivial, but finite better-quasi-orders are not trivial, as we will see. And in fact, they even appear in this proof of Fraïssé's conjecture. They're not just a curiosity, but they are relevant in the context of some important mathematics. Yeah, so now maybe that's already the conclusion then of this second lecture. Let's look at finite better-quasi-orderings. So first of all, how do you see that any finite order is a better-quasi-order? The answer is the open or Clopen-Ramsey theorem. Namely, the open-Ramsey theorem tells you that if you have a continuous coloring from this set of infinite sets of natural numbers with n colors, then this will have a homogeneous set, an infinite homogeneous set. So you will have the same constant color on the subsets of some infinite y. And for fixed number of colors, this is equivalent to arithmetical finite recursion. A corollary is that every finite order is a better-quasi-order. So why is that? Well, because let's consider such an f going into a finite order, and then you find an infinite y such that your f is constant on the subsets of this y. So in particular, you get that f of y is the same and hence bounded by f of y minus, because y minus is a subset of y. It's y without its first element, so it's a subset. And this was precisely the condition on better-quasi-orderings in terms of continuous functions, right? So there it is, the middle of this slide. You have a better-quasi-order precisely for every continuous function. You find an x such that f of x is bounded by f of x minus, and for the x you can take this homogeneous set. And it seems like having a homogeneous set is way too much, because you only need the same value twice here and not for all these subsets of y. But okay, in particular, you have this proof here. There's maybe a small thing that's irritating about this corollary. So here I said for fixed n, this can be done in ATR0. And here I'm saying in ATR0, every finite order, so the quantification over n became internal. But that's in fact true. So the corollary is really provable in ATR0 for reasons that I might explain later. But it's not clear yet why the quantification can be internal, but it can. And now you can ask, well, isn't this a bit excessive? You just want to show that a finite order is a better-quasi-order. You only need one such equality. Isn't a bit too much to use the open-Ramsey theorem, which is equivalent to ATR0? Can you maybe prove this corollary in a weaker system? And the answer is, for two-element orders you can, and I will show you the proof. But for three-element orders you cannot. And this is what we will show tomorrow. So if the antichain with 3 elements is a better-quasi-order, then you have at least ACA0 plus, so you have at least omega jumps. So okay, maybe it's not clear yet whether you need all of ATR0. Open, at least in published work. I'll say more about it tomorrow. I think there's work coming from Gent that might have or might soon solve this. But in any case, for 2 elements it's easy, but for 3 elements it requires quite a lot of logical strength. So let me maybe clean the blackboard, and then we can look at the proof that for 2 elements it's easy to see that this is BQO in the sense that RCNO can do it. So we want to see that any order with just 2 elements is a better-quasi-order. The hardest such order is the 2-element antichain, the hardest of the 2 that exist. The other one is linear. We already know that linear orders. So orders with 2 elements. This will ultimately boil down to the triviality that odd circles are not too colorable, and let's see how this goes. We consider a function f which goes from some block into a 2-element set, 0, 1. And now we start by picking 2 sequences in this block. We're trying to build our odd circle. Such that you have the following configuration. So you have this finite sequence S. And you pick some number n, which is larger than anything in S. And then you pick another sequence T in your block, which has only numbers above this number n. Right? And you can do that because, I mean, the S is just anything from the block. It's a finite sequence, so you have some number larger than it. But then the numbers above that form an infinite set, and any infinite set has an initial segment in the block, so you can take that. Okay. And then the idea is that you now want to move from S to T via the triangle relation, and you will do that in 2 different ways. The first way is you include this number n, and the second, on the second way, you do not include this number n. Okay, let me maybe clean the other board. So you will take, starting with S as R0, sequences that follow each other in this triangle relation. And let me say that in the first way you do this, you reach T at some stage k plus 1. And in the second way you do it, you reach, let's call these primes. R0 and R0 prime are the same, but then they will start to differ. And with the prime sequences, you will already reach T at step k. And I think I would just want to draw it. So let's say as in the picture. So what do you have to do? So the R1, the next thing on the first root, should be in the triangle relation with S. So it should overlap S, and you want to include this n. So the R1 includes this n and then maybe goes some way into T. This is your R1. And why can you find that? Again, because just take any infinite set that starts with S, n, and T, and then extends this in some way. This will have an initial segment in the block, and this is the R1. And they are in the triangle relation because S and R1 overlap except on the first element as opposed to in the triangle. And then you just continue in that way. So R2, you omit the first element of R1. You draw it like this. You again include this element. Maybe it goes quite far, so this is R2, and so on. And once you have omitted all the elements of S, and have then also omitted in the next step this additional element n, you will have reached T, And this is because in your black block, you cannot have two different things where one extends the other, right? So, and if things are initial segments, all the things that you pick are initial segments of the extensions of that thing by some fixed elements, then you will have to arrive at something that is and on the other route, well, you start in the same way, but you do not include this n here. And that you can also do because if you omit the n, it's still an infinite set, and you can pick initial segments of that. So let's maybe say the R1 prime looks like that, and so on. And the point is that the length of these groups, the number of triangle relations, differs by 1. So one is some k, and the other is some k plus 1. And this is because, well, in each triangle step, you omit one element, and here on the first root, you have to omit all the elements of S plus then also this element, this number n. And in the second root, you don't take this number n, so you only have to. That's why length differs by 1. Okay. And now you have your odd circle going from S to T in k plus 1 steps and then back to S in k steps. So it's 2k plus 1 steps. And just to write this down, so if your function f was bad, then f of Ri would always be different from f of Ri plus 1 because they stand in a triangle relation. And so if f is bad, they cannot be in the order relation, in particular reflexivity, they cannot be the same. But you only have two elements in your order. So you swap between 0 and 1, and the same for the primes. But then let's say k is even, then in the first root you have swapped even plus 1 odd many times. So you have swapped the number, you have changed the number. On the second way, you have swapped an even number of times, you have had the same number. So f of t would be different from f of t. That's the argument. Right. Yeah, and I wanted to show this proof because, to see that the two-element orders are bqo. I don't know if it's easy, but it's certainly elementary in the sense that RCA0 can do it, for example. And I think it was very much conceivable that the same could be done for 3 elements, just by finding a somewhat more complicated but still elementary graph-theoretic argument. But it turns out that this is not actually true. You cannot just do more intelligent combinatorics. You also need to bring in more logical strength. And that's what we'll do tomorrow. Not sure if I should continue a little bit, but let me maybe first ask for a question. Yeah.
Are there any
Good question. So what I can tell you is the two-element orders are easy, as we have just seen, whether you take blocks or barriers. And if you have the 3-element anti-chain, then even over RCA0, you gain a lot of strength regardless. So whether you use blocks or barriers, you can go from RCA0 to AC0 plus, and then of course you have Equinix lemma, and then things become equivalent. In this sense, I would say that the answer is no, but might of course be that there's something very subtle that maybe let me just show you. I've also put some reading recommendations. I think for the first part, there are just these, right? Yeah, but these are also on the slide. So this is the survey by Jan Pequeno that I mentioned earlier, and it uses somewhat different terminology from what I did, but it's really very nice. Then for the reverse mathematics, there are 2 survey papers by Alberto Marcon, and this is the later one, and it will probably cite the earlier one. So the later one is not quite an extension of the earlier one, and it makes sense to read both of these early papers, but I put the newer one because it cites the other one. And then this is the paper by Antonio Montalban that I tried to summarize, and it's really a very nice and readable paper. So very well read it now. It relies very strongly on this result by Alberto Marcone that better-quasi-orders are pi12 complete. So you ACA not. Maybe less, but ACA not is fine. And so if you have a pi12 formula and you want to form the set that it defines, then that gives you a family of quasi-orders indexed by the natural numbers. And to form the set by comprehension, you want to find out which of these quasi-orders are better quasi-orders. And then I don't quite remember, but I think you put descending sequences on top of them, and then you use the minimality in the minimal bad array lemma to detect whether they are better quasi-orders or not. Because if they are better quasi-orders, then the only bad part is this descending sequence that you put on top, and then your minimal bad arrays will stay in these top descending sequences. But if they are not better quasi-orders, then the minimal array should move into the given quasi-order itself. And I think you can then use this minimal array to detect which of the given orders is a better quasi-order. But it's so maybe some of you know this result by Steve Simpson and Alberto Marcone about the leftmost path principle. In ill-founded trees, you have a leftmost path that is equivalent to pi1 comprehension, and that can then be used to show that the minimal bad sequence lemma from the theory of well quasi-orders is also equivalent to pi1 comprehension. And somehow what we do is not quite the same as this, but we think that our proof could also be used to prove the other, which is much earlier. It really comes from this result that we'll try to show, that if you only have ACA not and ACA not more than that, then you don't even know that 3-element anti-chains are better quasi-ordered. And in fact, we have a complete characterization. So in theories weaker than ACA 0 plus, like ACA 0, the finite orders that can be recognized as better quasi-orders, they are precisely the ones that look like this. So they consist of 1- and 2-element anti-chains, and these are linearly ordered, right? So you place these anti-chains on top of each other. So precisely the finite orders that are recognized as bqo in these weak theories. And what this means is that, for example, the easiest order that is not recognized as a better quasi-ordering weak theories is this one, right? So you don't need a 3-element anti-chain. It's enough if you have a 2-element chain and 1 element that's incomparable of that, and that's not of this form. And so in these very weak theories, to find the minimal bad array, essentially you just have to find the minimal copy of this inside your order. That's the reason why the minimal bad array lemma is weak over these weak. Thanks very much.